So to get the formula for integration by parts, I mean, the formula's given in the book, but it's relatively easy to derive, so let's have a go. If we start with y equals uv, where u and v are functions of x, we know from before that dy by dx equals u dash v plus uv dash. Let's make uv dash the subject here, so we get uv dash equals dy by dx minus u dash v. Integrate both sides, we get the integral of u v dash dx equals the integral of dy by dx, which is y, which is uv, minus the integral of u dash v. So this I would memorize. Okay. It's in the formula book, just so that, just for reference, the formula book obviously doesn't use the u dash v dash notation, so it would look like the integral of u dv by dx, which is, that's v dash dx equals uv minus the integral of du by dx v dx. So that's how it's given in the formula book. But if I were to be trying to memorize this, I would memorize it in this form. It's a lot simpler, isn't it? Now, to help yourself remember, just look the patterns in this formula. There's no v dashes in the right hand side. So whichever element you label as v dash, you are going to integrate it. Essentially, you integrate it twice, because you integrate to get v, and then you integrate v again over here. The reason this works is because if u is something like x, when we find u dash, that just becomes a constant. Whereas the product with an x times some function is not possible to integrate, once we've got rid of the x by differentiating it, it will integrate. So obviously this won't work on any product, like every product. I mean, it won't work on every product like the product rule for differentiation does, but it does work when u dash v is simpler than uv dash. Okay, so should I copy this, seeing as how we're going to be using it repeatedly? Let's have a look at some examples. Okay, so that's our formula. So what we need to do is assign the variables. So like I said, we always want to assign the product that is just the polynomial. So in this case, the x will be u, and root x plus 1 will be v dash. Okay. It does matter which way around we assign them. It won't. So we want the u part to vanish, essentially. So if we write at the side here all our parts, we've got u equals x. Now that means that u dash equals 1. And we have v dash equals x plus 1 to the half. So here is where our integration by inspection skills come into play. We want to be able to integrate something like this in our heads, because otherwise it gets, if we have to do substitutions here, it gets too complex and you have to write down too much stuff. So this is just a linear. We've got a linear term in the bracket, so that means we can integrate this just by doing the chain rule backwards. So we add 1 to the power, and divide by the new power, and then divide by the derivative of the bracket, but that is just x. Okay, so they're all the pieces we need for our formula. So we're going to be doing uv minus the integral of u dash v. And in practice, really, that's all you need to memorize, uv minus integral of u dash v. So that will become uv. So looking over at, oops, sorry, I've mislabeled that. This is v. So over here, uv is just x times that thing there. So we get 2/3 x times x plus 1 to the 3/2 minus the integral of u dash v. So the u dash is just 1. The 2/3 I'm going to bring outside the bracket. Just a habit. I tend to do that. I don't think in this case it actually makes it easier, but I just tend to do that. So now we have to integrate again. This first term, 2/3 x times x plus 1 to the 3/2, there's not anything we can do to simplify that. So we'll just leave it as is. And now we have to integrate again. So we add 1 to the power. So that becomes 5/2. Divide by the new power, which is 2/5, but that's going to be multiplied by 2/3 as well. So it becomes 4/15. And let's put the plus c. Okay. That's it integrated. We should get into the habit of factorizing. So we've got, first of all, 2/3 and 4/15. So the common factor there. So the common factor for the numerator is 2. And if we've got thirds and 15ths, the common factor there is 15ths. 15ths go into thirds and they go into 15ths. We also pull out one of those brackets. We want to take out the smaller one, the smaller power. So that will be x plus 1 to the 3/2. And now let's decide what we've got inside there. So we've got to multiply 2/15ths by something to get 2/3. So that will be 5. And the x plus 1 has already been taken out, so that's all we're left with. And then on the other bracket, we want to have 4/15ths, but we've got 2/15ths. So that's a common factor of, we take out 2. And there's an x plus 1 to the power 1 in there as well. So this is 2/15ths, x plus 1 to the 3/2. 5 minus 2x minus 1 is 4 minus 2x. And we've got another factor now of 2 that we can take out. So let's do that. We get 4/15ths, x plus 1 to the 3/2, 2 minus x. Okay, next question. So I wanted to show you the exception to the rule I said earlier. So when I was saying we need to assign the x term to u, we always do that except when we've got a natural logarithm. Whenever there is a natural log in the integral, we will call the natural log u, because when you differentiate natural log of x, you get 1/x, and that 1/x will cancel. So we're going to call, but usually we would make the x term u. Okay, so that's u and v. And so u equals log x. So u dash is 1/x. V dash is x. So v is x squared over 2. Okay, so they're all the parts we need for using this formula. Incidentally, this is the approach that is used. I'm not doing it in this example, but you can do it yourself. This is the method that you use if you want to integrate just the natural log of x. If we get rid of that x and it's just log x that we're integrating, you treat log x as if it is 1 times log x, and you assign the variables like this. You call log x u, and v dash is 1, and then proceed, and you'll see. I recommend doing it because it's sort of a standard example that's used. Right, so here we go. Let's let's see if you can remember the formula. Try and write it down. So the right-hand side of that formula is uv minus the integral of u dash v. It's pretty straightforward, isn't it? uv minus u dash v. Okay, so uv then is log x times x squared over 2. So I'm going to write that as a half x squared log x minus the integral of u dash v. So that's 1 over x times x squared over 2. And here the x squared cancels with an x there. So we are left with a half x squared log x minus the integral of a half x. Again, normally I would take the half out, but I've just left it in. From the previous question, that taking the half out didn't actually make it any easier, so I'm just going to leave it this time. Half x squared log x minus 1 over 4 x squared plus c. And factorising again, we've got a common factor of a quarter x squared times log x minus 1. Okay. Okay, so in most cases, when you're dealing with a product, the two things that multiply together, one will be a polynomial in x and the other one will be some function of x, and then you assign u to the polynomial function. There are some odd cases where this works with, very special kind of trig functions, because the causes and sines end up cancelling and stuff. Okay, so I can't remember how to do this, so this one's an interesting one. I think we want to I think we want to assign u is going to be cos x sine x, and v dash is going to be cos x. This might not work, we'll see. So u is cos x sine x. Now cos x sine x is a half sine 2x. So u dash is cos 2x. V dash is e to the cos x. Now integrating e to the cos x. Right, okay. Let's try this again. We're now going to, I've just changed my mind. We're going to call cos x u, and we're going to call sine x e to the cos x v dash. So now u equals cos x. So u dash equals minus sine x. V dash equals sine x cos x. Sorry, sine x e to the x. E to the cos x. And now because we've got the derivative of the power in front, we could say that this differentiates to minus e to the cos x. So that's just using the integration by inspection. What we've got there is the derivative of the bracket in front of the bracket, except there's a minus sign missing. So to check that works, differentiate minus e to the cos x, you would get minus e to the cos x multiplied by the derivative of cos x, which is minus sine x. Okay, so now putting all this into our formula, we get uv minus the integral of u dash v, which is, I'm going to change to black, just to let so this is the actual answer. So uv is minus cos x e to the cos x. minus the integral. Now there are limits. We'll deal with the limits at the end. U dash v is minus sine x times minus e to the cos x. So that's sine x e to the cos x. How does that make this any easier? So this becomes, technically, for this to be correct, we should have the limits written on here as well. So let's 0.5 pi. I'm just going to sub it all in at the end, though. So this becomes minus cos x e to the cos x minus, so when we integrate sine x e to the cos x, we've already done that once, you get minus e to the cos x. Between 0.5 pi. So now sub in 1/2 pi, we get cos of 1/2 pi is 0 plus e to the 0 minus, subbing in 0, we get minus 1 times e to the 1 plus e to the 1. So that final answer there is 1. Right then, so again, as usual, could you pause the video and have a go at this one? If you'd like a hint, wait a little bit longer. So my hint is make u equal to x. Okay, now pause. Okay, so u is x, v dash is x squared. So u equals x, u dash equals 1, v dash equals sec squared. And v, now remember, this is a standard integral. When we differentiate tan, we get sec squared. So when we integrate sec squared, we get tan. Putting all that into our formula, uv minus the integral of u dash v, we get uv, which is x tan x, minus the integral of u dash v, so that's the integral of tan x dx. The integral of tan x is a standard integral that's in the formula book, log sec x. Okay, next we have x to the 4 log x. So again, pause the video and have a go at this. Okay, so this time, normally we would assign the polynomial the letter u. In this case, this would be awkward because we'd have to do integration by parts 4 times in order to get rid of the x to the 4. We will look at an example where you have to use integration by parts more than once later, but fortunately, the other function is log x, so we can just assign u to log x instead. We should do it that way as well. So u is log x, so u dash is 1 over x. V dash is x to the 4, so v is x to the 5 over 5. Putting all this into our formula, we get, okay, so uv becomes a fifth x to the 5 log x. We have limits here, so I'm going to write that on. And we subtract the integral between 1 and e of u dash v. So that's 1 over x times 1 over 5 x to the 5 dx And we have some cancelling here. The x to the 5 cancels with that x. So this will become, let's work out this first part. So we can sub the limits in at the very end if we want, or we can sub it in two chunks like this. So it's a matter of preference really. So this first bracket, if I sub e in there, we get a fifth e to the 5. And then log e is, so log is log base e, so e to the 1 is e, so it's 1. And we subtract, well, when we sub 1 in there, we get a log 1, so that just becomes 0. So this will be subtracting the integral from 1 to e of a fifth x to the 4 dx. So this becomes a fifth e to the 5 minus 1 over 25. Sorry, not e, x to the 5 between 1 and e. And we get a fifth e to the 5 minus 1 over 25 e to the 5. Take away 1 over 25 times 1 to the 5. Okay. So we've got 1 over 5 e to the 5 minus 1 over 25 e to the 5. So that's, and we've got minus 1 over 25. So we get minus 1 over 25 is 1 over 25. A fifth is 5 25ths. So we've got 5 25ths minus 1 25th. So that becomes 4 25ths e to the 5. And we could just take out 1 over 25 as a common factor there. Okay, next. This one involves a couple, you have to do integration by parts twice. So if you want to have a go, pause the video. So we will assign u to the polynomial term and v dash to the other term, as usual. So if u is x squared, u dash is 2x. So the x hasn't vanished, so we're going to have another product in the integral. So we'll have to do integration by parts again. So v dash is e to the x. Fortunately, v then is just e to the x. Relatively straightforward example. And we are going to do uv minus the integral of u dash v. And that will be uv is x squared e to the x. This is between 0 and 1. Minus the integral of u dash v. So this is 2x e to the x between 0 and 1. And we have to do integration by parts again. So now we're going to call this term u and this term v dash. So u is 2x, u dash is 2, v dash is e to the x, v is e to the x. I'm just going to sub all the numbers in at the very end. For no particular reason other than show you it doesn't matter at what time you do it. So this becomes, so it's uv, so that will be 2x e to the x minus the integral of u dash v, so that's 2 e to the x dx between 0 and 1. This is between 0 and 1. Okay, so let's use just one pair of square brackets here for everything. So we've got x squared e to the x minus 2x e to the x. And now we've got minus the integral of 2e to the x. So that's plus 2e to the x. And the whole thing is between 0 and 1. Sub in the 1, we get e to the 1 minus 2e to the 1 plus 2e to the 1. take away, well, any term with an x in it will vanish here because we're subbing in 0. So we're just left with the 2e to the 0, which is 2. So we've got e minus 2e plus 2e minus 2, so that becomes e minus 2. Okay, we've got two integrals here which are related. So we're going to do part 1 and then use that to calculate the answer to part 2. Okay, so pause this and have a go. I'm just going to make them a bit smaller. Okay, so for part 1, we make u is x, u dash is 1, v dash is sec squared, so v is tan x. So uv minus the integral of u dash v becomes uv is x tan x minus the integral of u dash v, so that's tan x dx. So this becomes x tan x minus log of sec x. Again, that is in the that one is in the formula book. Plus c. So for part 1, the integral of x sec x is x tan x minus log of sec x. Now for part 2, our u will be x, so u dash is 1. So v dash is tan squared x. So yeah, so now we've got a little bit of work to do here. In order to integrate tan squared, we're going to need to use the identity 1 plus tan squared x equals sec squared x. Okay. So v dash is sec squared x minus 1, which means v is the integral of that, which is tan x minus x. Okay. So our integral uv minus integral of u dash v will become uv, which is x times tan x minus x, minus the integral of u dash v, which is tan x minus x dx. And here we can integrate this. This becomes log of sec x minus x squared over 2 plus c. So this becomes x tan x minus x minus log sec x plus x squared over 2 plus c. Okay, there are a couple of ways to maybe sort of simplify this a little bit. I think with the way the question was phrased, I would probably leave the answer like this. However, we have got a couple of x squared terms, so we could collect those together to give us x tan x, and then we've got minus x squared plus x squared over 2, which just gives us minus x squared over 2 minus log sec x. Now, that is perfectly acceptable as a final answer. I am going to show you, so the textbook I got this example from, it gives the answer, you could as minus log cos x. Now that's because sec x can be written as cos x to the minus 1, and then you bring the minus 1 in front because of the laws of logarithms. So yeah, I'm not going to do that. I don't think that it's necessary, but obviously it's worth knowing that trick, because if a question said show that, you get the answer here with a plus log cos x. You need to be able to convert log sec x to log cos x by using, the laws of logarithms with a power of minus 1. So that's the video on integration by parts. There'll be plenty more of these to practice in the video that's coming up soon, where integration practice, where we will look at lots of past exam questions. So see you.